Good day, everyone. This is Jeff Babbitt. I'm an account architect here at Fujitsu. I hope everyone's having a great day. So today, I would like to talk to you a little bit about the history of telecom. A while ago, I had a interaction with someone who had just recently took a history of telecom course, and they were very underwhelmed, did not think it very helpful to them. And that caused me to start thinking about how would I present the history of telecom, and this is the outcome of my musings. So this is basically the history of telecom according to Jeff, and hopefully you'll find it helpful. Telecom absolutely started with Alexander Graham Bell in 1876, who invented the telephone. That was the beginning of our industry. What Mr. Bell did is he figured out how to encode voice signals into electrical signals, send them across a wire, and then reconstruct the voice at the distant end. And this is what the first telephone looked like. A few years later, around World War II, we had a phone system in this country, and it was very analog oriented, and it was very manual oriented. You had a phone, a crank phone like on the left here. My father remembers having one of these. You didn't have a phone number, you would have, a combination of short and long rings that you would do with this crank. He clearly remembers their phone number was 3 longs and a short. And that wouldn't connect you to another person. Oh, shoot. Let me start over again. So let's skip a few years forward to around World War II. We had a phone system in this country. It was very analog oriented. There wasn't dialing plans. There wasn't all sorts of the neat things we have now. But what you had was a phone that looked like the picture, this one on the left. It didn't have a dial. You would ring a combination of long and short bell, 3 longs and a short. My father clearly remembers his phone number was 3 longs and a short. And what that would do is that would connect you to an operator like the young lady in the middle picture here. And you would tell her who you wanted to call. And she would actually connect you to that person and ring them, and they would answer the phone. And not only was it very manual and analog like this, but it was actually a party line. You would have multiple homes on a single line, and people did listen to other people's phone calls. That's just the way it was back then. Very large central offices like this one here had huge banks of those analog connections and operators to do these connections for you. In the bottom right, there was a television show in the 70s called Laugh-In. And this is Lily Tomlin, a comedic actress, who on that show did a series of sketches where she was the local operator, and the things she would do just were hilarious, and they still are quite funny. She would answer the phone a lot and say, "Is this the person to whom I'm speaking?" I don't know how you answer that, but she had made fun of that, and it was quite interesting. Then a little bit further along, the Undertaker steps in. Now, not this Undertaker in the purple picture from the World Wrestling Federation. It was actually a mortician in a small town. His name was Stroger. And Stroger, there were 2 morticians in this small town. And it so happened that the wife of Stroger's competition was the switchboard operator for the town, and he was convinced he was losing business because people would call in and ask for the mortician. Even if they asked for him, he was convinced that she was connecting most of the calls to his competition. He said, "I need to find a way to automate this so that we don't have the wife stealing business from me." And he invented what is called the Stroger switch. It was a mechanical switch that would connect your call to someone else. Not long comes a dialing plan now with the rotary phone. And as the rotary phone, you would dial the number, it would connect you to that their call. So very mechanical. Interstate and between cities would still require that switchboard operators, but your local area could now be automated. And some of these systems at the central office with these mechanical switches very large, like this picture on the right now. Also, since they were mechanical, they made noise, click, click, clank, clank, and this room would have been deafening to be inside this room with all of those noisy calls. But it was the next step in automation and efficiency. Each one had their own line. You could dial other people around the city. Still had to use an operator and a switchboard to get between states and to other cities. But that's the next step that happened in the process. Then comes something quite interesting. The digital revolution happened. The digital revolution, one of these steps, I don't know which one you want to call it, it was the beginning of the digital revolution. It's kind of a series of technological steps. In 1947, Moore at Bell Labs, Brattain and Moore, demonstrated the first semiconductor transistor. And a semiconductor transistor is simply an on-off switch that allows current to flow. You can turn it on or off. Prior to this, we had things, they were called vacuum tubes. And if you remember the pictures of the old shows, or if family might have an old vacuum tube radio or television, they were large boxes that had these big vacuum tubes and would glow and hum and warm up. But then someone created that same device. That vacuum tube was basically, but it was large. It was the size of a Coke can or a pop can, and someone created that in a piece of silicon. And this is very small. It's the side of the inside of your pen, a straw, essentially the side of a straw that's less than a half inch long. It's a cylinder, and it's three pieces of silicon creates a switch. Then a few years later, Shockley, who worked with Brattain and Moore at Bell Labs, created his own company and developed the same thing as a transistor, but it's on a piece of silicone, a flat piece of silicone, and it's called a field effect transistor. And same thing, it's an on-off switch, it's a transistor, but it's flat, it's planar. There was a large number of people, 8 people that worked with him. They all left him. That's from Shockley Semiconductors and started Fairchild, and Fairchild started Intel, and Intel and AMD, and they took this technology, and Intel used this field effect transistor, and in 1971 they put 2,300 of these little transistors, squeezed them onto one little piece of silicon, and created the first microprocessor, a 4-bit MPU microprocessor. And in my opinion, this is where the digital revolution occurred. This allowed all kinds of things to happen. In fact, those 8 guys that left Shockley were referred to as the traitorous 8, and they formed upwards of family tree of 65 different companies in electronics and technology in that California, the Silicon Valley, and that's hence the term Silicon Valley, from all these companies, and resulted in like trillions of dollars worth of business activity because of these people. And they created all these microprocessors that permeate everything. This is where the explosion of the digital nature came. This allowed us to create transistor radios instead of those big radios. It allowed us to shrink the size of televisions, develop VCRs, permeate our electronics into cars. Electronics is everyone now. And let me describe some of the explosion that happened from this first microprocessor and the subsequent things that they created. The most obvious one from the microprocessor is an explosion in computers. We started off with mainframes and PDP-11 VAXs and supercomputers, and then the PC came along, and then cloud computing, and I have some of those. There was a movie called Hidden Figures, where NASA was launching the space station in the 60s, and they had people, individual people, that would do all these calculations for trajectories and reentries of the space modules entering the Earth and going to the moon and everything. And they got one of the first large IBM mainframe computers, a 7090 and 61. And this is a picture. The picture on the left is Octavia Spencer, who played the lady that programmed that computer for NASA. And the picture on the right is the actual picture of the lady in front of her computer. It's a fairly accurate depiction of what was going on back then in the first use of the large mainframe computers. But that resulted in supercomputers and the small computers and cloud computing, a huge explosion, all because of the development of that first microprocessor. If you have lots of different computers, then there was an explosion in software. Started with Fortran and BASIC, C, Python, HTML, Java. Many people know this much better than I did. I first learned Fortran and BASIC when I was in high school and college, and now everyone's learning all the different kinds of languages that there are now. It's just an explosion and created the entire industry of software engineering. Came from the need to control these microprocessors. Then these computers were first deployed in research institutions at universities and various other research institutions. And these institutions had a need to communicate with one another so that they could send information back and forth. And so the first thing they needed to do is, I want to send a file from one city to another, from one computer to another computing environment. Someone created a protocol for that called File Transfer Protocol, 1971. It's FTP. Not long at that, someone came up with the idea, I would like to send a little email, a concept. I want to send a message to one of the guys at the other facility so we can discuss what we're doing. So they created the simple mail transport protocol, and it's called SMTP. The beginnings of the networking industry were these actions and these creations here, and that led to TCP/IP, and both FTP, SMTP, TCP/IP, they're still with us today. It wasn't just protocols, it was also the devices to be able to send traffic between these files and these messages between these things. And someone came up with an Ethernet switch. Bob Metcalf did in 1985. And then routers came along 1986, and then MPLS switches. So the development of that first chip created an entire industry of networking and all these different devices using these kinds of chips. And so that integrated circuit led to an explosion in consumer electronics, computers, software, as well as networking, which is what Fujitsu and the ICT and the telecom industry is all about, is connecting different computers and people together through our telecommunications system. And that's our industry now. It all came from Alexander Graham Bell, the development of digital chip technologies, and we apply that to do the things we're doing now. One of the things we did to the telephone system is we went from that analog system with those Stroger switches and those operators to a digital format. So these phone calls are now digitized, and we ended up with a push button phone instead of a rotary phone here. And with the development of digital switching technology in the 70s in this country, it was the digital switches. All of those banks of operators and banks of Stroger switches were replaced with digital phone switching systems, like a picture one here. This one's a DMS 100 system built by Nortel, and then the 5ESS by Bell Labs and Western Electric. Those two dominated the system. There were a couple others, but those two dominated the telephone system in the 70s, 80s in the US. I want to point out, at this point in time in the 70s here, everything was still electrical signals on a copper wire. We're going to talk about optical, but that's emerging at the end of the 70s and beginning of the 80s, and I'll talk about that next. But everything up until now, it's all taking that voice or these messages, putting them on an electrical wire, a copper wire, and sending them across to wherever your destination is. Now, before we get to the optical side of that, from the beginning, there has been an inexorable demand for more and more information across that wire, across this system. We started off with a small number of phones, and then we had party lines with multiple people on each phone. And then by the time you get to the 70s, almost everybody has their own dedicated phone. And that phone is connecting to everyone. So you can not only call your neighbors, you can call businesses, you can call your work. So the number of phone calls has been growing dramatically from the development of the phone and the first deployed phone systems. And that has resulted with a system by which your phone would connect to an aggregation site. That aggregation site would go to a central office to where one of these operators were, or then in the 70s, one of these DMS, these digital switches were at the central office. And then you would have to connect with a wire to other central offices across the state or across the country to connect it to wherever your destination call was. Now, as you get more and more and more calls, you can't be doing one call on a wire. The demand said between these central offices, I need more calls on a single wire. I need a lot more wires. So you could just deploy a lot of wires, individual wires between each of these central offices. That wasn't very efficient. So they devised a mechanism, Bell devised mechanism in the late 50s where you could aggregate a group of individual calls onto a single wire, and it was called a T1. So a line with a single call on it was called a DS0, a digital subscriber loop level 0. And what they did is they would aggregate 24 calls onto a wire and send that wire to the next central office. And that connection was called a T1. And that worked for a while. And someone said, there's even more calls going on. We need even more calls on an individual wire. And they developed a DS3, where they took 28 of those DS1s and put it on a T3. And so that T3, each one of these calls is about 64 kilobits per second. The T3 has 672, 24 times 28, 672 calls. It's about 50 megabits per second, 45, 50 megabits per second. And that's where, if you hear these terms, a DS0, a DS1, a T1, or a DS3 or T3, this is what's going on here. You're aggregating individual phone calls into a single connection on a single wire at a higher data rate. And this is how we could accommodate even more and more phone calls. And that was driven through the 50s, 60s, and 70s. And these central offices, most every town has a central office somewhere downtown. It's usually a big, square, ugly concrete building with no parking lot, a small parking lot, no windows in it. Here's a picture. Now, I live outside of a town called Plano and Allen, and this is a picture. These are downtown Plano, downtown Allen. It's just a square building, and it was these big rooms that originally housed those big banks of Stroger switches, and then those switches were taken out, and big banks of DMS digital switches, the 5ESS or the DMS 100s were in there, and huge, just bunch of electronics go on there to switch all of these calls automatically. Nowadays, if you go in there, it's the equipment that handles these calls is much more compact. So a lot of these rooms that had those big banks of switches are only half full of electronic equipment because the equipment is much more dense and can handle a lot more traffic. It's quite interesting. But so you will all find one of those central offices. It's not well marked, but they're just a big building downtown. Now, we continued to have the growth of phone calls and required even more capacity to it. And we needed even more. And someone discovered light. We can use light to do this. In 1962, someone created the first laser. The first laser was demonstrated in 1962, but it wasn't very useful because it took a huge tank of liquid nitrogen in order to keep it at the cold temperature so you could get this lasering action. It could actually require that it would actually generate light. But this is when the first laser was created. Then we have Star Trek that did some wonderful things with lasers there. And then it took another decade where in about 75, the first room temperature semiconductor version of this. So this was actually done at room temperature on a silicon, just like those transistors were, and you could actually make this silicon create laser light. It would emit laser light like the drawing on the right here shows, that you could actually, using the right amount of electronics and the way of building these semiconductors, you could make it emit laser light at room temperature. And so this was the development of the optical communications industry. It took a little bit longer to figure out how to turn that into a useful product, but the first development here was this room temperature semiconductor laser. So what do we talk about when we talk about a fiber optic system and using light? What would happen is you would take a fiber optic cable, which is shown on the left here, and it looks like a fishing wire. And if you take the end of that fishing wire and you connect it to the part of that semiconductor that's emitting light, you can now shine light. You can now control the light pulses going down that fiber. And what we found is that you could then encode that same digital data that Alexander Graham Bell encoded into an electrical signal. We could take that electrical signal and code that data into light pulses and send those light pulses down this fishing wire, fiber optic cable, to the other end and recover that communication signal. Why would we do that? Because you can go further than you can with an electrical wire before you need a boost. You can also put more information into light than you can put on a electric wire in electrical. So this again, as we needed more and more capacity, we started to deploy more and more fiber to carry that traffic because you could get more traffic on there, you could go a longer distance. This is kind of shown on the little illustration on the right there. Essentially what's happening is you have a guy with a flashlight, which is that semiconductor laser, and he's flipping that thing on and off very, very fast, like millions of times in a second, kind of like doing Morse code with light, shooting it down that fiber. And on the other side of the fiber, you can receive those light pulses and recreate that digital signal and do that. And then it's bidirectional. You got to have them doing it each way. This is something called on-off keying, and that's the way light systems first worked. And it was first deployed in 1977. They deployed a commercial using fiber optics to do telephone with a 6 megabit signal in Long Beach, California. I actually had a very interesting conversation with a retiree at another company that what he claimed was the first commercial deployment of a fiber optic system in the US in about the same time frame. His was a 50 megabit per second, a single DS3, which is 672 phone calls between two central offices. They thought that was great because that was a lot of capacity. It was wonderful, but it was just the start. Just a second here. Okay, now that we have this fiber optic signal, in the same way back then when you had a wire, they needed a mechanism to put multiple phone calls on it called the DS3, the DS1, and the T3, T1 architecture. We had to do something like that for light, and it's called, along comes synchronicity. It's called synchronous optical networks. No, not the Police album from the 70s called Synchronicity. I actually had that album there, but it's synchronous optical networks. And it's a set of standards that define how you can put data into this light. You can aggregate different phone calls, whether it be a phone call or whether it be an internet system or data system or whatever you want to go across there. You can put digital data, whether it be phone calls, video, voice, anything, into this fiber optic, and you can do different rates. And so this particular Sonnet standard, which is still in use today, it has different rates, how much data I can put across this single fiber. And those different rates is called OC, an optical connection, 3, 12, 48, and 192. And OC 192 is 10 gigabits worth of data. An OC3 is 150 megabits, and it's just aggregating more and more traffic, turning that light on faster and faster. The OC3, your light is going on 50 million times in a second. The OC192, your light is going on and off 10 billion times within a second. You push a lot of data across there. This is the first place where I'm going to tie it into Fujitsu. FNC helped the industry move from asynchronous sonnet systems to this sonnet standard, asynchronous optical systems, to this sonnet standard here in the 90s. And the first products we developed to do that was called the FLM family of products, FLM 400, 600, 1200, 2400. We followed that up with a FlashWave 4100, FlashWave 4500, so that after the FLM products were becoming quite successful for us, we helped the industry move to Sonnet. They decided to come up with a new brand. We called it the FlashWave brand. So subsequent products for the next 20 years were the FlashWave products. And these were all based upon the Sonnet standard. Then we had to learn to embrace the wave. No, we're not surfing in California. The internet came along about this time frame, the 2000s, and created even more digital demand for our telecom network. So not only is it the phone calls that are still going up, but now we have email, now we have internet, you're purchasing things, a huge increase in demand for the telecommunications network. How can you get even more traffic onto these wires and these fibers? Well, a technology called DWDM, dense wave division multiplexing, came to our aid to help us get even more traffic across this fiber. In order to illustrate that, I want you to think about if you happen to take physics in your high school or college class, and if you can't remember that, don't worry about it. I'll explain it without having to go through a physics class. I will they utilize a technology called a prism. A prism. So a prism is shown, this one happens to be on the 1973 album from Pink Floyd's album called Dark Side of the Moon. This was the first compact disc I ever bought. And this is your first lesson on optoelectronics was the cover of this Pink Floyd album. And it shows a prism. What a prism does, according to your physics class and this album, white light goes in. White light is actually composed of many different colors. And it breaks it out into the individual colors, red, yellow, green, blue, and violet. Is very much what happens if you see a rainbow. The same thing's happening in nature in a rainbow. The water molecules in the air form a prism. White light comes out, breaks it off into the different colors, and hence there's the rainbow. But you can also do that with a little device called a prism. It's a piece of glass that will do that. What they were able to do is shrink that down to where it was very small. And what I could do is I could take one of these fibers, so that guy with that flashlight there, that's shining that flashlight, I'm going to turn his light from white light into red light. I'm going to turn the next fiber, the next guy down below him into green light, and the next guy down below him into blue light. This prism will take those three colors, put it on that one fiber, send it to the other side, the other destination, the other city, the other central office. Another prism will break it apart, and we can recover the red light so that you can, in this case, you're putting 3 times the traffic on that single fiber. Now, today's systems were doing 128 colors on a single fiber. So this was a huge way to increase the capacity on a fiber optic cable and reduce the cost per bit dramatically. So in the mid 2000s, FNC introduced our first DWDM product. It was called the FlashWave 7500, dense wavelength division multiplexing. Now, what has happened with the industry so far is everything's carried on these fiber optics. From your house to an aggregation site might be copper. If it's cable, it could be a hybrid fiber coax. Even if you're using a cell phone, you're only wireless from your handset to the antenna. At the bottom of the antenna is what? A fiber. They put it onto a fiber. So they put things, all this traffic gets put onto a fiber as soon as you have enough traffic to warrant putting it onto a fiber because it's much cheaper. You can go much further. It's a better way to handle this traffic, much less lossy. There's all kinds of things that are involved that drive you. So fiber optic system is really ubiquitous across the country. Fiber optics goes to every DSLAM, every hut, every central office, every data center, every tower, wireless tower. They're all connected with a fiber optic system. And all of this is part of our telecom system. So this was the next advancement in technology in the history of telecom, was the introduction of fiber and the introduction of DWDM, so you could put multiple waves across there, increase the amount of capacity that was going across this system. In addition to these transport technologies I've been talking about, there's always been a problem in telecom. I got an individual call coming from my house or my business office or that tower. How do I aggregate them so that I can send that across this fiber optics, this telecom infrastructure system? Back in the 70s, 80s, and 90s, there was a slew of access aggregation technologies that are listed here. The vast majority of these have all died and gone away. And across this time, so that it was challenging back then to deal with all these different kinds of technologies. What has evolved across time is only four of them are really left standing. There's something called Sonnet. We talked about Sonnet. That still exists, but it's kind of shrinking. Uh, OTN is a next generation Sonnet. It's basically Sonnet and steroids. And it does have a market, but it's kind of limited. There was something developed called Fiber Channel. Fiber Channel was pretty much driven by the need for financial institutions. I needed to do something that was very secure, very low latency, and very fast, and Fiber Channel was that. And so it's still there, but it's kind of a niche market. The one that has garnered the most usage is Ethernet. What comes out of your laptop is an Ethernet signal. All that communications, you send it on the Ethernet, send it to the internet. So now they just use that Ethernet to carry that traffic all the way through the system now. And even with your cell phone, once your cell phone communicates through your wireless technology to the antenna, it gets put on Ethernet onto a fiber to get it to the mobile switching center to connect you to your end user or to connect you to the internet. So Ethernet has the one that's grown to become the most important access and aggregation technology, with these other ones being niches. So I just wanted to share that thought with you a little bit. And I want to finish off by talking a little bit about Fujitsu's products in this space across these time periods, the most recent end of that time period. So I talked about in the middle, in the blue box on the left, that the Sonnet products, we started with the FLMs, 4100s, 4500s, and those products were very successful. They just did Sonnet, uh, uh, the Sonnet communication for the cross-synchronous optical networking. Many of these products are still deployed and being used today. Many, they're all over the place, but they have been manufactured discontinued. We don't make them anymore. The chips that we buy from our components vendors, they stopped making the chips. We had to stop making the products. And then we also came up with more efficient ones. When it came to DWDM, the 7500 is a Fujitsu product that was shown there on that middle right blue box. We had a couple of partner products that were in the FlashWave series that also helped us. The product that is very popular right now, still being sold, 7500 happens to be manufactured discontinued, is our FlashWave 9500, and it is still our dominant product right now. It does a combination of things. It does some of that DWDM. The transponders of turning a signal into colored light. That's a transponder. It has cards in it that'll do WDM, these prism type technologies, and these transponders. We have Ethernet switches in there. We have OTN switching in here. We have Sonnet switching in there. It's called an aggregation that does a lot of different things, and it's very popular and being deployed everywhere. In addition to that, on the bottom, we have a variety of little access products. The FlashWave 4100 ES did Sonnet and Ethernet, and the FlashWave CDS also did Ethernet. Different ways of aggregating traffic and putting it onto this network. So this was pretty much with the software associated with it, our hardware portfolio through the 2000s up until recently. And then what I'm going to do in the next session that I do is I'm going to introduce our new groundbreaking premier technology product portfolio called the Onefinity portfolio. And I'll talk about the Onefinity portfolio that's going to take us from what these products, moving us to the next stage into the future. So thank you guys very much. I hope this was all beneficial to you also and you learned a lot, and enjoy your day. Thank you very much.